Edwin Hubble discovered that Andromeda is not part of the Milky Way and expanded our universe exponentially. He classified galaxy types, and neither of those is what he's really known for. What he's really known for had to do with measuring distances to galaxies, again, like he did to Andromeda, but to galaxies at larger distances. So we're starting to measure distances at which finding Cepheids becomes difficult. With today's technology, we can measure Cepheids out to, as I said, maybe 10 million parsecs or 20 million parsecs, but at the time this was still difficult. Astronomers needed ways to measure distances to galaxies. Galaxies are easier to see than Cepheids that are more luminous. What you'd like is a period luminosity relation for galaxies, and indeed there are such at least approximate relations. For spiral galaxies, the Tully-Fisher relation relates the rotation velocity in a galaxy to its luminosity, and there's a Tully-Fisher relation for every type of galaxy. So SB galaxies have a different Tully-Fisher relation than SA galaxies, and so on. And roughly the idea is that larger galaxies are more luminous and have larger rotational velocities, and you see here the accuracy with which this relation holds. It's not a very accurate distance measurement, but it tells you that if you can measure with Doppler shifts the rotational velocity of a galaxy, you can classify its type from its shape. You can now figure out the luminosity of the galaxy. You have galaxies as standard candles. These are very brilliant standard candles. Indeed, you can see them out to very large distances, and you can measure distances, because if you have luminosity and you measure brightness, you can figure out the distance to something. There's an analogous relationship for elliptical galaxies, which allows the distance to ellipticals to be measured. Today, at larger distances yet, we can measure with type 1a supernovae, but remember that if you want to measure the distance to a galaxy in which, alas, there is not a type 1a supernova that has been observed, then you are reduced to variable stars or these kinds of methods and refinements thereof. So using all these methods, Hubble goes around and he measures the distances to many galaxies, and of course, trying to understand how they work, he measures their spectra. And these spectra take a while to identify because galaxies are moving at rather high velocities relative to each other, and therefore some are approaching us at high velocity, some are receding at high velocity, and you have a case of big red shifts or big blue shifts, and you need to figure out which spectral lines are which. Astronomers, as I said, are very good at spectrometry, and what Hubble finds when he starts working through these spectra is that as he looks farther and farther out into the universe at galaxies that are more distant, less and less of them appear to be having negative radial velocity, moving towards the Milky Way. More and more of them appear to be receding, and furthermore, the farther they get, the faster they appear to be receding. And so here's a nice plate with an example of the shifted spectra that Hubble is measuring. So here are 4 images of 4 galaxies. They appear smaller as they get more distance in these negatives. And here are their spectra compared against some standard spectrum above and below. And we're looking for some particular line of potassium here. And what we see is that the farther the galaxy is, the farther to the red this line is shifted. And the bottom image gives you a sense of how good these guys were with spectrographs, because it's not totally obvious that this little gap right here is a spectral line, and furthermore that it is the potassium line, and it turns out that it was. And so with these, Hubble can relate the known wavelength of the potassium line to the wavelength at which he measures it. He can use the relativistic version of the Doppler shift formula or the Newton approximation non-relativistic expression. Both of those are things we're familiar with by now, and he can convert the observed redshift into an observed recessional velocity, and the statement that the redshifts are increasing with distance is the statement that the farther a galaxy is, the faster he observes it moving away from us. So here is Hubble's collection of data from the paper that he published, and what we see here, the horizontal axis is distance, the vertical axis is recessional velocity, radial velocity. We see that here's a galaxy that's actually approaching the Milky Way. That is fine. But that the farther you get, the more the galaxies are all receding, and Hubble very bravely draws a straight line through this bit of data, and declares that he's found a relation between distance and recessional velocity known as the Hubble law. This is what he's famous for. The recessional velocity of a galaxy is given by a constant, Hubble's constant, times its distance from the Milky Way or the Sun. It's the same thing. And Hubble's constant is therefore a conversion of distance to velocity. So one way to express its units, because that's the way we measure it, is in kilometer per second recession per megaparsec distance. And Hubble has an estimate for the value. This estimate has been refined over the years. We have a lot more data. But this constant is of such importance that long before its exact value was known, astronomers needed to use it in their expressions. And so they developed a method of sort of parametrizing their ignorance. The Hubble constant is characteristically written as 100 times little h kilometer per second per megaparsec. In other words, if someone were to measure the Hubble constant and its value were to be discovered to be 100 kilometer per second per megaparsec, we'd say little h is 1, and we'd go around into all the formulas and all the books and papers that have various powers of h in them and set h to 1 and get an answer. But at the moment, until we're absolutely certain of the value of the Hubble constant, people use this little h to parameterize the dependence on that measurement, because so much depends on this, as we shall see. But the value of h is not too far from 1. We now have far better measurements than Hubble had. We've measured much more statistics. The most recent measurements suggest a value of h on the order of 0.71, and as you can see, we know it quite accurately. We have here a plot of recent measurements in the vein of Hubble of recessional velocity as a function of distance out to 1.6 billion light years away, so 500 megaparsecs. And we see that Hubble's linear relationship holds up very, very well. What's exciting about this plot is that little rectangle at the lower left. That represents the data that Hubble actually had. So he was predicting the straight line velocity on the straight line plot and its slope on the basis of a very small amount of data, and was gloriously vindicated. Now, typically in astronomy, we write the Doppler shift as lambda is 1 plus z times lambda 0, and we call z the redshift. So z is a positive number, and assuming something is redshifted, and z equals 0 is a redshift of 0, in other words, lambda equal to lambda 0. And so clearly z is related to velocity. The expression is written down here. Let's figure it out. So lambda divided by lambda 0 is 1 plus z, and lambda divided by lambda 0, remember, we had lambda divided by lambda 0 is the square root of 1 plus v over c. This is the completely relativistic formula. And this is supposed to be 1 plus z. So the first thing I do, of course, is I want to figure out how z determines v. And so I want to solve this for v over c. And the first thing I do, of course, is I square both sides. And I write that 1 plus z squared is equal to 1 plus v over c over 1 minus v over c. Then I multiply both sides by 1 minus v over c, and I find 1 minus v over c times 1 plus z quantity squared is equal to 1 plus v over c. And then I move all the v over c's over here, so I have v over c times 1 plus z squared. And then everything without v over c goes over here, and that's 1 plus z quantity squared minus 1. So I solve for v over c, and I get that v over c is 1 plus z squared minus 1 divided by 1 plus z squared plus 1. And again, if z is small, if the redshift is small, you can use Newton's approximation to show that this is approximately z, which is indeed, when this is approximately 1 plus v over c lambda 0, then z is approximately v over c, but this is the exact relativistic expression. So astronomers will rarely tell you, unless they're talking to the hoi polloi like us, that an object is at a distance of 2.8 billion parsecs. They will tell you that it has a redshift of 0.3. The reason is that we'll see next week that distances are ill-defined, but certainly redshifts are measured observable quantities, and the farther an object is, as long as Hubble's law holds, the larger its redshift, And so we basically can speak about redshift as a surrogate for distance. And indeed, the Hubble law tells us, remember, we solved for v over c as a function of z here, but the Hubble law tells us that v over c is the same as h0 d over c. So if you know z, you can figure out d as well as v. So knowing the redshift tells you not only the speed, obviously, with which the galaxy is receding, but also its distance. So we have to digest this. In whatever direction we look, galaxies are receding from us. The rate of recession does not depend on the direction of the galaxy. Galaxies at the same distance at all directions are receding with an equal velocity, but the farther they are, the faster they are receding. Now, depending on your taste, you can either conclude that we're an unpopular galaxy, or, more technically, that we're in the center of some cosmic expansion. Everything is moving away from us. It turns out that this is not exactly correct. Your intuition is in this case actually misleading you. Imagine this collection of galaxies here. They are all going to be moving away from each other. The center of expansion could be the center of the screen. Or if I take this and add to it a motion of everybody to the right, the center of expansion could be way over to our left. Each galaxy, as it observes each of the others, will see that each of the other galaxies is growing farther or farther away from it. So all that is going on is that as these galaxies grow farther and farther away, all of their distances are increasing. And the fact that in this case it looks like the expansion is about the point at the center of the screen is completely irrelevant. They're all moving away, and the farther they are, the faster they are moving. There is no centrality involved. This is just the way it is. So, we need not invoke some particular central location for ourselves. Everything is moving away from everything else. All distances are growing. Every observer, as he looks around him or she looks around her, will see all other observers receding. And the mathematical expression of this is that if you measure any distance in the universe at time t0, by t0 I mean now, and then you measure it either later or earlier, if you measure it later, it will have grown by a factor which depends on time in this fashion. What this tells you is that over a time t, distances grow by an amount that is h times d. Oh, yeah, the speed of recession is h times d. Now, this is valid both into the future, and of course this didn't just start happening now, so it's valid into the past. If t is less than t0, if you're looking into the past, then this is a negative number. Distances in the past were smaller than they are now. Fine, if everything is receding, that means everything used to be closer together. I should point out immediately that what we're seeing is that galaxies, all distances between all galaxies, appear to be growing. This does not mean that the distance between, say, the Earth and the Sun is growing, first of all, or that my belly is growing. That's not cosmic expansion. This is a description that is valid for objects too far away to be gravitationally bound. The Earth and the Sun and the Milky Way are all moving as one object. The Milky Way is not, in particular, expanding. This is the motion of distant galaxies that are not gravitationally bound to each other. It's to that case that the Hubble law applies. The other point is that, of course, there are still peculiar motions. Galaxies are still orbiting various things, and that they do on top of this global expansion. So everything is expanding, but that is not necessarily the only motion that galaxies do. So, for example, one could ask, if everything is expanding, how do galaxies collide? That is a case where their peculiar motions are larger than the Hubble expansion for the relatively small distance between them, and that usually happens in cases where they're gravitationally strongly interacting or bound. Okay, so Hubble gives us this picture where the entire universe is growing. Every galaxy is receding from every other galaxy. What's it growing into? What is beyond the place where these galaxies are now? More of the universe. The galaxies are receding into the universe. We'll talk about the sort of mathematical implications of this expansion a lot next week, but at the moment, there need not be an edge to the universe in order for all distances to grow. All we have is a bunch of galaxies that are receding from each other, and beyond them are probably more galaxies that are receding even faster from where we sit, and no matter which galaxy you sit on, everything recedes at a rate proportional to its distance, because all distances grow by the same factor. This is the symmetric picture. Okay, so Hubble teaches us that all distances are increasing. right from there, you have a big discovery. Look, this can't have been going on forever, because if in the future distances are going to be bigger, as I said in the past, they're going to be smaller, and farther in the past they were smaller yet, and farther in the past they were smaller yet. Oh, and at some point in the past you can solve the equation that says d of t is 0. The distance is 0. Which distance? It doesn't really matter. If I make this factor 0, all distances are 0. All of the galaxies that we see and the ones that are too far for us to see, as we sort of look farther and farther back in the universe, come closer and closer, and the farther they are, the faster they're moving. They are now moving away from us, so into the past they get closer, and at some point everything is on top of everything else. There is a time at which all distances are 0. What is that time? Well, solve the equation. 1 plus h times t minus t0 is 0. Move the 1 over to there. You find that h t minus h t0 equal to minus 1. And so what does that tell me? That tells me dividing by h, I call that h0 inverse and cross out the h's over here. And I find that t is equal to t0 minus h0 inverse. Wait, so h0 inverse is a time? I thought h was something in kilometer per second per megaparsec. Well, once you remember that a megaparsec and a kilometer are both distance units, you realize you can convert one to the other, and indeed, kilometer per second per megaparsec is 1 over seconds times some small number, or megaparsec per kilometer per second. The units of h0 inverse are indeed the units of time. So what is this time? This is the so-called Hubble time. It's very important. This is the time where, if you imagine that this equation governs the universe, this is the time in the the time into the past at which everything was on top of everything else. So let's compute it. The 100 gets converted to 0.01, h converted to h inverse. This is the inverse of a kilometer per second per megaparsec. A megaparsec is how many kilometers? Well, a megaparsec is this many AU, and an AU is this many kilometers, except I've also, while I was at it, introduced megaparsec. So there's 10 to the 11, and then this is how many kilometers a megaparsec is, and then the seconds come out. I plug in all the numbers, I get this number. If I allow multiply it through, I get 9.8 h inverse. If I plug in the most recent value for h of 0.71, I get, finally, my result for the Hubble time, 13.8 billion years. What is this? Well, this is the maximum amount of time the universe can exist, because before that, at that time, everything was on top of everything else, and I can't go farther back than that. So we have a finite age for the universe, given Hubble's expansion, and this is our rough and ready estimate for how old the universe is. It turns out to be surprisingly good. We will need to improve it. It will turn out that this precise behavior is a Newton approximation to some more complicated time dependence of distances, and that'll be the topic of next week. But first, we can get even more out of this story. Remember that the redshift z determines distance, at least for small z, where the Newton approximation holds, as v over c is 1 plus v over c is z. Remember that v over c was supposed to be z, and v over c is therefore h0 over c, d over c, and so d is zc over h0. So if you know the redshift, you can figure out the number, the distance. This allows you to figure out something else, though, something called the look-back time. If a galaxy is a distance d away, then what I am seeing is the light that left that galaxy a while ago, and the farther the galaxy is, the longer the light has taken to get here. The Andromeda galaxy is 2.5 million light years away. We see the Andromeda galaxy as it was 2.5 million years ago. The farther an object is, the farther back in time we see it. The look-back time is simply the time that the light was emitted is t0, which is our notation for the present, minus d over c. This is how long it takes light at the speed c to cover that distance. Plugging in the value for d, we get that the time we see a galaxy at is t0 minus z times h0 inverse. Again, z is the fraction of the Hubble time. if you want, a fraction of the age of the universe that has passed since the light was emitted by this galaxy. This gives us another exciting way to think about things. Let's think about it this way. So remember that I'm going to compute the wavelength at which light was emitted divided by the wavelength at which I'm going to observe it. This is kind of backwards to the usual calculation of the redshift. The redshift is lambda observed divided by lambda emitted. So this is actually 1 plus z inverse. It'll be clear why I'm doing it this way. Now, I'm going to assume that I'm in the reasonably small redshift neighborhood of non-relativistic motion, so that this expression is correct, first of all, and second of all, that because I can use Newton's approximation, because z is much less than 1, then I can use Newton's approximation to approximate 1 plus z to the minus 1 as 1 minus z. Okay, and then from here I have an expression for minus z, which says that this is equal to 1 minus, to get minus z, I take h0 times minus z is plus h0 times t emission minus t0. Oh, but I know what 1 plus h0 times t minus t0 is. Remember that our expression for the Hubble change in distances was d of t is d of t0 times 1 plus h0 t minus t0. Oh, good. So this is exactly d at the time of emission for any distance divided by that distance at t0. Okay, so what do we have? That the wavelength at time of emission divided by the wavelength we observe is which is 1 minus z approximately, is the same as distance at the time of emission and distance now. Which distance? Doesn't matter. They all scale by the same factor. Write that out cleanly, and now you see that it's telling me something. What is this? This is a distance, the wavelength. This is telling me that the wavelength over the time between emission and observation or absorption has scaled the same way any other distance would. So Hubble's redshift formula is basically telling me that the wavelength of a light wave grows along with the distances between galaxies. That's a very strange way to think about it. We'll see next week that it's very natural. This is thinking of the redshift not as a Doppler shift, but as a cosmological shift. The wavelengths of light stretch just like any other distance. We'll come back to this next week.